Hey guys, so in this video we're going to be going over inverse functions. We're going to go over how to compute the inverse and also the graphical representation of what an inverse actually is. So let's get started. So here we have that an inverse function blank another function. Other than the word of being the inverse of the function, right, what that actually means that an inverse function cancels out the original function. So we're going to put here cancels out the original function. And we're going to look at it here as if we input over here, if we input g into f, what it does is that it gives you x. So what that means that if f and g are inverses and you input g into f, you're going to get x. But what is x? X is the original input, right? And the same thing goes for when you input f into g. So what we can say about this, let's think about a function again as a car wash, right? And if a function is a car wash, which means that you input a dirty car and you output a clean car, the inverse function, what it's going to do is that if you input a clean car, it's going to go back to being a dirty car, right? So let's kind of represent that here when we have the blue little loops here, that we're going to say that if in your function, your clean car is going to be A, right? So if you input A into your function, you're going to get 3. So A is your dirty car, A is your dirty car, and they're going to output your clean car, which is 3. Now in your function, in your inverse function, if you input 3, which 3 is your clean car now, if you input it through the function, which is now the opposite of a car wash, you're going to get A, which is your dirty car. So we're going to refer to A as your dirty car. We're just going to say dirty. And then this is clean. And then we input clean and we get dirty. So that's the idea of an input function. Of an inverse function, my bad. So now here we have the notation for the inverse function is f of f to the negative 1 of x. So this is not 1 over the function, it is f to the negative 1, right? So next, along with these loops that we have here, these little circles, well, they're ovals, I don't know what you want to call them. So there's also, we're going to talk about the domain and the range. So if you guys see here, the a is corresponding to the 3 in the function, but if we go into the inverse function, the 3 is corresponding to the a. So what that means is that the x's and the y's flip. And when the x's and the y's flip, the domain and the range are also going to flip. So what we're going to say is that the domain of f of x is actually the range of the inverse function. Alright? And with that being said, the range is also now related to the domain of the inverse function. So the domain and the range flop. So graphically, how are we going to show this, right? How are we going to show graphically that a domain and a range are going to switch, that an x and a y are going to switch? So graphically, the inverse is a reflection over the blank line. The magical line here is going to be the y equal to x line. So we're going to draw that right here in our xy coordinate, the x equal to, the y equal to x line. And we're just going to draw this function that you guys will soon learn about, the exponential function. And we're going to say that it goes through we're going to call that 0, 1. So before I draw its inverse function, which is going to be the function that I'm going to reflect over this, whenever you have a graphical representation of a function, you can check real quick if it has an inverse in the first place, because it may not have an inverse, right? So here's where we throw in the horizontal line test, right? So to be a function, it needs to pass the vertical line test. But now to be an inverse, it needs to pass the vertical line test plus the horizontal line test, right? So it needs to pass 2 tests now, which we're gonna test it real quick in green. Vertical line test is only going to touch once wherever we draw vertical lines, and horizontal line test, if you guys can see, it's only going to touch once if we just draw a bunch of horizontal lines all across. So this is what we call a function has an inverse if it passes the vertical line test and the horizontal line test, but that is only when we ask the question graphically, right? You guys will see now if the function has an inverse when we compute it in the example right above. So now let's jump right into actually computing the inverse of this stuff graphically. Now that we know that it has an inverse because it passes the vertical and the horizontal line test, now we're going to see how the inverse will look. So we have a point here that's very valuable to us. We have 0, 1, right? But like I told you guys, when we compute the inverse, the x and the y are going to flip. So here we're going to draw this in, let's go back to green, okay? So now that we have 0, 1 in the function, the inverse function is going to have 1, 0. You guys see how the x and the y are just going to flip. So I'm going to draw a point through there. And believe me, I'm not a magical sketch artist here. But if we reflect every point, it's just kind of like, if you guys see, it's like the same distance from this line. The same distance this way, same distance this way, same thing, and so forth. Our lines are going to look like this, right? So now we have in blue, we have the original function, and in green, we have the inverse. Graphically is what it looks like. But let's go into how to do it with just the function, right? If they give me the function, how am I going to actually find the inverse? And to compute the function now here in our next section, all we're going to do is we're going to follow the step box that I have here. So 4 quick steps, and you have the inverse of your function right away. So let's first start with the first step, right? So we're going to write step number 1. We're going to change this f of x we have here for y. So we're going to write it in, let's go with blue. So blue is equal to y equal to 3x plus 2. So what I have here, actually this is way too crammed, 3x plus 2. And this is not like a real step, changing it from f of x to y, but it's sure going to help and make us follow the steps faster, right? So if they give it to you in y, you're 1 step shorter. If they give it to you in f of x, just add this little extra step number 1, where you change it from f of x to y. So right after step 1, we follow step 2, which tells us that we're going to switch x and y. So here we have y, and then here we have x, and all we need to do is just kind of switch them around, right? So I'm going to go with blue again. So now I'm going to have x equal to 3y plus 2. Before I had y equal to 3x plus 2, now I have x equal to 3y plus 2. So this is the whole switching of domain and range, the whole switching of x and y. It's input right there. So now we're going to go to step 3, where we say we're going to solve for y. So what we want, right, our goal is to have y by itself. So now we want to solve for y. So when I mean solve for y, I just mean leave the y by itself. I'm going to move over the 2. So it's going to be, I'm going to subtract the 2 from both sides. So it's going to be x minus 2 equal to 3y. And then I'm going to divide by 3 on both sides. And now that I have y by itself, I have achieved y by itself. I'm going to go into step 4, where I'm going to change its notation for like a little final touch. I'm going to change its notation to f inverse of x equal to x minus 2 over 3. Now, let's say you just want to be like crazy, you know, like impress your professor, be like, wow, this guy really has his algebra skills on point. You can go ahead and do this. You can divide the x by 3 and divide the 2 by 3, so you get x over 3 minus 2 over 3. So now you have computed the inverse, and you have simplified and made it look all pretty. Now, let's go into computing the domain in part B of the inverse, right? So we look at our inverse function, right? Our inverse function here is still a line. It's x to the first power. And what we're going to do is think about a line. What is the range of a line? Actually, let's just go into the domain right now. What is the domain of a line? The domain of the inverse, right, which is our line, the domain is just going to be negative infinity to infinity, because a line has no restrictions on its domain. However, now let's say we didn't have an easy domain to compute in our inverse. What we can do is we can go back into our original function, our original f of x, And we can ask ourselves, what is the range of this function, right? So now we can change colors, just, you guys are bored of blue, so am I. We can go into f of x, right? And then ask ourselves, man, what is the range of f of x? And we ask ourselves, what is the range of a line? So a line is actually a very easy function, right? And it has no restrictions in the domain, and it has no restrictions on its range. So therefore, the range of a line is negative infinity to infinity, and it's also going to be its domain. So here we have that the domain and the range are exactly equal, because that's how you find the domain. The domain is actually the range of the original. So if you're ever stuck on the domain of the inverse, you can just go back to its range, to the original function, and use it to find the range. So that's how we find the domain of an inverse. And let's say you want to go into the checking process, right? They're always going to ask you, there's a quick way of just asking you, if you know what an inverse is, right? They're going to test you, is this an inverse, right? So you got to know, like, oh, it's an inverse if I input g into f, and if I input f into g, and it gives me x. So they can test you on if you know how to do inverse. They can also test you here on how well you can do composite functions. So it's kind of like a 2-in-1. So it's very important that we go over it, right? And also, if you guys notice here, our f of x, right, is 3x plus 2, which is our f of x that we just used, and our g of x is the inverse that we just got, right? So now here what we're going to do is we're going to check if what we did, if I'm not lying to you, in letter A. So what we're going to do is we're going to start off by computing f of g of x. So we're going to do f of g of x. I'm going to start off with the same way I do composite functions, which is I leave a big parentheses where the x's are in the original function, in the parent function, like I like to call it, and then I'm going to input my function. In this case, I am inputting g into f, so I'm going to put g of x in here. I'm computing f of g of x, and I'm going to write g of x where my parentheses is, so 1/3 x minus 2. Now, no, I don't like that sideways. Let's do this. So now I am going to distribute and check if I get x. So now I'm going to distribute this into here. So let's make this 3/1. So I multiply straight. 3 times 1 is 3. 1 times 3 is 3. So 3/3 is 1. So 1x or just x. Let's actually put this in red. And now I'm going to distribute the second number, which is 3 times 2 is 6. 6 divided by 3, 1 times 3, which is 3. So it's 6/3 just gives me minus 2. Just gives me minus 2. And then I have a plus 2 outside, which I'm going to just go ahead and cancel this negative 2 and this plus 2, giving me an answer of x. So my f of g of x is clear for x, so I am halfway done to checking that this is an inverse, that I did my work correctly in the previous A. So now let's do the next part, which is g of f, let's leave that open still, g of, and let's go back to red, sorry, g of f of x. So I'm going to have 1/3, big parentheses where I'm supposed to input my function, and then 2/3, and I'm inputting f in this case. I'm going backwards, right? I'm inputting f into g, so I'm going to put f of x in here. I'm going to have f of x, which is 3x plus 2, right? Now I'm going to have 1/3 times 3 is going to be 3/3, or just 1x, or just x. That looks like weird. So just x. And then that was the first part. And then 1/3 times 2 is going to give me positive 2/3. And then I'm going to just join the outside. This outside here, this negative 2/3, which is going to cancel out the positive 2/3 and the negative 2/3. And it's just going to give me x as my answer. So therefore, I have x for both, and if I get x for both, that means that I have computed, that means that both functions are inverses, and I'm good to go. Therefore, this is the way that we checked the first example that we did by the proper method of checking, which is finding both the composites, f of g of x and g of f of x. So now let's move on to something different, not same kind of examples that we've done. Let's look at some radicals and some parabolas. So here we're going to have two functions, right? Radical of x minus 2 and square root of x, an x squared minus 2. So let's go ahead and do the first part, which is f of g of x. Once again, here we're going to have big parentheses where the x is, minus 2, all under the radical. And now we're inputting g into f. So we're going to do f of g of x. So we can input here x squared minus 2. So therefore, when we simplify, we have x squared, and you see this negative 2 and this negative 2 don't cancel because they're not opposite signs. They actually add, and they give us a minus 4. So since f of g of x, which was our first one that we tested, didn't work, that's enough to tell us these two functions are not inverses, right? They're not inverses. So here they are inverse. So yes, happy face. And then here, no, sad face. All right. So now I'm going to give you guys some more challenging practice problems on how to find inverses and how to check them. So look out for the practices coming up right now, and see you guys next time.